Okay, so today we talk about the absolute convergence and ratio and root test. So this will be the last two tests, ratio, root test. And this can be a confusing concept. So let me give you an example what we're trying to achieve in this section here. Let's look at this series here. As we know, this is what we call alternating series because the sign is, alternating. And we know this guy converges by alternating series test because the positive component, so here's the reason, okay? Positive component is 1 over n, decreases to 0. Alternating series test says, this series converges. And notice this is not a positive series. This is a series with mixed signs in there. And now let's try to take the absolute value of all the terms. We get a positive series. So I take the absolute value. Now this is the harmonic series, and we know this guy diverges. So I can say the original series converges, but the absolute value series diverges. Let's look at another example. Same reason. This is also an alternating series. The positive part also decreases to 0. So this one converges as well by the same reason, okay? Same reason. And now let's take the absolute value of each component, which make this a positive series. So what about this guy? Well, this is actually the p series. This is the p series, sigma 1 over n to the power of p. Whenever the power of p is bigger than 1, this one converges, okay? The p here, in this example here, the p is 2. So we know this one converges as well. So we can say the original series converges and the absolute value series converges as well. So for those two series, they behave a little bit differently in the sense that if you take the absolute value, the first one will diverge. If you take the absolute value of the second one, it'll converge. So we're going to call this one, okay, even after you take the absolute value, it also converges. We call this one converges absolutely. This one is a different story. So a series, it'll be a series with some negative terms in there. Then I can take the absolute value. Okay, so we call this absolutely convergent. If the series of absolute values converges. So just put the absolute value sign on both sides of all the terms. Is convergent. So the original one may be a series with some negative terms in there, but the absolute value series, for sure, is a positive series. For example, the example that I presented earlier, that's the sign switching part. That's the positive part. This one I know is convergent absolutely, or is absolutely convergent. Because Well, by definition here, because if you take the absolute value, you get this P series with P equal to 2, because this guy converges. Okay, and that's why we call this one converges absolutely. And the other example that I presented up there is this one. So the positive part is 1 over n. So this one is not absolutely convergent. Well, because we take the absolute value, you get sigma 1 over n. And we know this one diverges. Okay? And that's why we say this one is not absolutely convergent. So now I'd like to introduce a concept for a series where the absolute value does not converge. And this is what we call converges conditionally. Conditionally convergent if the series itself is convergent. Okay, if the series itself has to be convergent, if it is convergent. Now if the series itself diverges, then we simply call it diverges. Okay, we simply call it diverges. A series is called conditionally converges if it is convergent, but not what? So that's the part we need to fill in here. But not absolutely convergent. Okay, but not absolutely convergent. That's what we call this one converges conditionally. Okay, that's when I call this guy converges conditionally. So that's why the earlier example that we presented, like this guy right here, this one right here, this is conditionally convergent or converges conditionally. Conditionally convergent. And let me show you the reason, okay? Because the series itself converges, because itself is convergent. Once again, that was because of alternating series, but not absolutely convergent. Meaning, if you take the absolute value, which result in this harmonic series, but the absolute value series diverges. In other words, not converges absolutely. All right, and that's why we call this one converges conditionally. Okay, converges conditionally. So these are the two concepts. Obviously, does not give us any test to check if it converges absolutely or conditionally. It's just a concept. So I'd like to give you a few more examples to clarify this concept. Let's think about this guy. This one converges absolutely or conditionally? Yes. So obviously you have to take the absolute value of this thing and check it out, okay? Let's take the absolute value. You get a series like this, which by now we know this is a geometric series, okay? It's a geometric series. And the common ratio, R, is one half, isn't it? R is 1/2. That's the ratio between two neighboring terms. So this one converges. And that's why we call this one what? Is absolutely convergent. Okay, it's convergent absolutely. And because of the absolute value series converges. Okay. Here's another example. So once again, by alternate series test, this guy itself converges. Okay. So we're trying to fill in the results here. Because the series itself, because this guy converges. Alternating series test. And now let's take the ops value. That's 1 over 2n plus 1, okay? And then we can do a quick limit comparison test to find out this guy actually diverges. So the series itself converges, but the absolute value series diverges. And that's why we call this one is conditionally convergent. All right. So for those who are wondering, why this one diverges, you can do a limit comparison test. Okay, limit comparison test works like this: do the limit between this series that you have with something that you know about, like 1 over n, sigma 1 over n. You let n goes to infinity. So you can calculate this by yourself. Okay, this limit turns out to be 1/2, which is a non-zero finite number. So whenever it's a finite number, so it'll behave the same with sigma 1 over n, which we all know diverges. So that's why this guy diverges. Okay, that's why this guy diverges. All right. So these are a pretty important example that helps you to understand the meaning of this. All right. One last example is this one. Let's look at this guy. Well, if you this is obviously another ordinary series. Unfortunately, the positive part does not go to 0. The positive part, which is n over 2n plus 1, does not go to 0. Instead, it goes to 1/2. So we're gonna say this guy simply diverges. Okay, this guy diverges by, can you guess what test? Diverges by test of divergence. Test of divergence says as long as the term here does not go to 0, then the series must diverge. So for this one, it simply diverges. We're not going to talk about convergence conditionally or absolutely. It simply diverges. All right, simply diverges. So now let's move on to some results. If the series itself is absolutely convergent, all right, so think about what that means. Okay, that means the absolute value, take the absolute value of all the terms, that new series converges. The result claims then the original series, okay, a sigma a sub n, must also be convergent. So absolutely convergent implies convergent. If a series converges absolutely, they must be convergent. So think about that. Here's one example. Let's find out whether the following series converges or not. So sigma sine n over n squared. We're talking about sine 1 over 1 squared, sine 2 over 2 squared. Now find out whether this guy is convergent or divergent. Notice here I'm not asking if this guy converges absolutely or conditionally. That's not what I'm asking here. I'm asking whether this one converges or diverges. So many of the tests we had so far, including direct comparison test and also limit comparison test, as well as the not so convenient integral test, all of those three tests can only be applied or applies only to positive series. Okay, positive series. And the other series test, which is alternating series test, well, applies to the alternating series, where the signs keep switching from positive to negative and then positive to negative. Now this guy, however, sine n over n squared, it is clearly not a positive series because there might be some negative terms in there. I just don't know where it is. In other words, for this series, I cannot apply direct comparison test, I cannot apply limit comparison test, and I cannot apply integral test either. And moreover, I cannot apply alternating series test either because this is not switching in signs. This guy can be positive, this guy can also be positive. So it's not necessarily switching in sign. Put it simply, all the tests that we had so far, simply it's not going to work here. Okay, simply it's not going to work. So let's see how this will help us. So let's find out what happened to the absolute value series. So let me write down a brief solution here. So now I'd like to take the absolute value. So that's the absolute value of this term. Once you took the absolute value, this guy become positive or not negative. So I can apply the direct comparison test. I can apply limit comparison test to this new guy, okay? And obviously I can compare it with 1 over n squared. The fact that sine n is always less than 1 says this is always less or equal to 1 over n squared. Because this is less than this guy, and we all know this one converges. So that's the smaller one, that's the bigger one. So I can say, if you take the absolute value of all the terms, this new series converges by what test? By what test? Direct comparisons, directly compare with 1 over n squared, so by direct comparison test. And this statement right here, okay, sigma sine n over n squared absolute value converges. This statement, it is equivalent to say this, okay, it is equivalent to say the original series converges, well, absolutely. Absolutely. Well, our previous result says any series that converges absolutely implies the original one converges. So that's how we come up with this conclusion. Thus, the original series must be convergent. Okay, converges. Converges absolutely implies converges. Okay, and that kind of makes sense because converges absolutely means you take the absolute value of all the terms, making everything positive. That turns out to be a finite number. That obviously implies the original one that may have some negative terms in there, definitely smaller than this. Is that this guy is definitely smaller than this? It must be convergent. Okay. So now I'm gonna move on to the last two tests, namely the ratio test and the root test. The ratio test. The ratio test says if you take a sub n plus 1 divide by the previous term, so this is a ratio between two neighboring terms, and you have to take the absolute value here, meaning a sub n does not have to be, well, positive. It can have some negative terms in there. So you calculate the limit of this ratio here. If this turns out to be some constant that's less than 1, the ratio test says then the series that you're looking at is absolutely convergent. And notice this is a very strong statement. Absolutely convergent means if you take the absolute value, it's also convergent. As our previous theorem says, if a series converges absolutely, it must also be what? Convergent. Okay, therefore convergent. Depending on what you're asked, if you're asked, hey, is this series converge absolutely? You go ahead and say this one converges absolutely. If the problem says, is this series converges? You're also going to say, yes, it converges. That is, provided that the limit of the ratio here is a number smaller than 1, okay, like 1/2, 1/3. If this is some constant that's bigger than 1, then it turns out sigma a sub n. Well, the conclusion is not that this guy is not absolutely convergent. The conclusion is actually this series actually turns out to be divergent. Okay, divergent. The third case is, what if the limit of the ratio is 1? Well, it turns out if this is 1, we can't say anything about the series. In this case, the ratio test fails or is inconclusive. What does that mean? That means we need some other test, okay? We need other test to deal with this problem, okay? We need additional test. So if you look at this ratio test, it appears to be very easy to apply. The reason is because you don't need to come up with anything to compare with. You don't need to think about this at all. You just look at the series itself. You write down a sub n plus 1, you write down a sub n, you do the limit of ratio. It's less than 1, absolute convergent. Bigger than 1, divergence. Okay? So it's indeed very powerful. Let me show you one example here. So n cubed over 3 to the n. 3 to the n. So n cubed over 3 to the n. That's what you're going to get when you take the absolute value. Okay, when you take the absolute value. If you think about the comparison test or limit comparison test, these are all comparison tests. So you have to pick something to compare with. But then it appears it's tricky for us to come anything to compare with this guy. So let's see how this ratio test works. Ratio test always start by writing down the limit sign, and then by writing down a sub n plus 1 over a sub n. All right. So a sub n refers to this whole thing. Okay, a sub n is this whole thing here. And don't forget, take the limit here. Now, because I'm taking the absolute value, so I can completely ignore the sign part. So let's look at a sub n plus 1. We're going to replace the n here with n plus 1. Am I right? So that's a sub n plus 1. Divide by a sub n, and that's a sub n. So multiply it with its reciprocal. So I have a 3 to the n on the top and cubed on the bottom. So the goal here is to find out the limit. So here's what I do. I'm going to piece those two guys together, put n plus 1 over n, and there's a power 3, so I can put that on the outside. So that's n plus 1 cubed, which is right here. The bottom is n cubed, which is back there. And we rearrange the order and put those two terms together, all right? Now let's find out what happens when it goes to infinity. N plus 1 over n, as we all know, this guy goes to, the limit of this is 1, isn't it? Right? N plus 1 over n goes to 1. And this guy back there, turns out we don't need to do any limit, because you can clearly simplify this. Cross off 3 to the n, cross off 3 to the n, you will get 1 over 3. So it's a constant, 1/3. The limit of the first component is 1. The number back there is 1/3. That's why the limit is just what? 1/3. Well, limit comparison test says the series converges. Well, absolutely. Okay, absolutely. End of the story. Okay, end of the story. So now I will do another similarly tricky example here. Okay. Let's look at this guy. So I know this is a positive series. Okay, I know this is a positive series. So in practice, I can apply the direct comparison test or limit comparison test. But it's just that it's hard for us to picture anything to compare with. If you can take a look, another look at this, we have a factorial on the bottom here. And even though this is a positive series, we can still apply the ratio test. Okay, we can still apply the ratio test. Ratio test did not say you cannot apply it if it is positive. It's just the absolute value will be the same as the original guy. Ratio test says if this is less than 1, then the series is absolute convergent. And notice the series itself is already positive, then the absolute convergent is the same as convergent, because it does not make any difference if you take absolute value. All right, so think about that. All right. So solution. Now I can tell the reason why the ratio test is so powerful, because I don't need to think about anything to compare with. I do the limit of the ratio here. And notice in this example here, I don't need the absolute value sign anymore because it's positive. So I write down a sub n plus 1. Replace all the n with n plus 1. Divide by a sub n, multiply with the reciprocal. Okay. The problem is it looks kind of tricky to calculate the limit of this ratio here. So that's the tricky part. So let's find out what the limit of the ratio is. N plus 1 factorial is n plus 1 times by n factorial. Okay, for those who are not familiar with this, I want you to write down what n plus 1 factorial is and compare it with n factorial, and you will realize this. So those two terms clearly cancelled. So on the top you have n plus 1 to the power of n plus 1. On the bottom you have n plus 1 times by n to the power of n. And we can simplify it further. Okay, we're going to simplify this further. Let's see. Here's n plus 1, this n plus 1 to the power of n plus 1. So I'm going to cancel out 1 n plus 1. And I have n plus 1 to the power of n on the top instead of n plus 1 because I'm going to cancel one of them out over n to the power of n. For this guy, we're going to take the power n on the outside. The top is n plus 1, the bottom is n. So it's 1 plus 1 over n to the power of n as n goes to infinity. So you can experiment a little bit with this number here and try to plug in some n that's big. Okay, try to plug in some n that's big. I know that 1 plus n goes to 0. Some of you may think, well, the base becomes 1, so the answer will be 1. But that turns out not to be the case. It turns out the limit of this is a very special number. The limit of this is the very special number, natural number e. Natural number e. So this is a result that you can memorize. 1 plus 1 over n to the power of n as n goes to infinity goes to e. Once again, you can experiment this by plugging in, say, n equal to 100 or 1000, see what you end up with. Well, so that's the limit of the ratio. Natural number e, which is 2.7 something, okay, 2.77 something. So that's bigger than 1. So what's the conclusion? Well, the conclusion is it diverges, okay, diverges. Diverges. And I'll do one more example. Factorial, there's another 2n plus 1 factorial here. So many of you can tell that this is a alternating series because of the sign switching here. And the positive part is 1 over 2n plus 1 factorial. And this guy clearly decreases and goes to what? Goes to 0. So actually I know this guy converges, okay? This guy converges by alternating series test. So let's find out how does this ratio test works and what does the ratio test tell us. So we're trying a different test. Limit of the ratio, okay? Limit of the ratio. So once again, I'm going to throw away the sign part here because I'm taking the absolute value. So let's think about a sub n plus 1. What is a sub n plus 1? It's 1 over now once again we're going to replace the n here with n plus 1. So it is 2 times by n plus 1. And replace the n with n plus 1. So this guy is a sub n plus 1. Divide by a sub n. So multiply with, well, it's reciprocal. So you got 2n plus 1 factorial on the top. The bottom here, when you FOIL this out, you get 2n plus 3 factorial. 2n plus 3 factorial is 2n plus 3, 2n plus 2, followed by 2n plus 1, and then 2n, and then all the way down to 1. So in other words, the term back there is actually 2n plus 1 factorial, okay? So now I can tell those two terms canceled. We get a 1 on the top, 2n plus 3, and then 2n plus 2. Now clearly the limit of this is what? 0, because the top is a finite number, the bottom goes to infinity, so it's 0, which is less than 1, okay, which is less than 1. If you look up the ratio test, the conclusion is it converges what? Converges absolutely, okay, converges absolutely, okay. So that's the ratio test, okay, that's the ratio test. The last bits I want to talk about is the root test. The root test somehow looks very similar. It's just what's involved is the root. Okay, it's the root. And this is the last test. Okay, this is the last test. You take the nth root. And notice this is sometimes this does not make sense. If a sub n is positive, okay, that's okay. But if a sub n is negative, but n is some even number like square root or fourth root, then this is undefined. So that's why to apply root test, make sure you take the absolute value of all the terms. If this limit turns out to be some number that's less than 1, very much similar to the ratio test, the conclusion will be the series converges absolutely. Number 2, bigger than 1, they diverges. And notice the conclusion is not, this guy does not converge absolutely, but diverges, okay, but diverges. Number 3, if L is equal to 1, it's inconclusive, okay, it's inconclusive, and you have to figure out something else to check this out. I'm going to show you a couple examples next. So same question, whether this series converge or diverge. Solution, take the limit of the nth root. Some of you might notice the reason we choose to do the root test is because this guy carries a power n. So if you do the root test, it'll cancel out this power. All right. So that's one criterion you can use to choose between ratio test and root test. Okay, depend on the format of the series itself. So you take the nth root, and also notice this is a positive series, so that's why I don't need the absolute value. It's the same. and then this is power n, this is the root, so they cancel each other out. So it gets something like 2n plus 3 over 3n plus 2. And the answer is 2/3. Okay, the answer is 2/3. Well, which is less than 1. So what's my conclusion? Well, the conclusion of the root test says this one converges what? Absolutely. But obviously I don't need that word here because the same to say this guy converges and converge absolutely. They're the same concept. Okay, same concept because this guy is positive. So I simply say this guy converges. Here's one last example. So once again, the function here is a power function. You got a power n on the top here. So we choose to do the nth root of the absolute value, and I do need the absolute value sign here because I got some negative terms in there. Take the absolute value, make this guy just 2 to the n. So once again, you can clearly simplify this. This is limit 2 over n to the power of n. That's what's inside. And then the whole thing raised to the power of 1 over n. And then multiply, you get a 1. Okay, you get a 1. So that's why you're looking at the limit of 2 over n. Well, which is 0. Less than 1. Okay, less than 1. So the conclusion is converges what? Yes, absolutely. Okay, converges absolutely. Converges absolutely. Converges absolute once again means this guy automatically converges. Okay, converges absolutely implies converges, but this is a very strong conclusion. And that's the end of it. So that wraps up 11.7 ratio test and root test. It's a very important section. All right, you need to distinguish the concept between converges absolutely and conditionally. And this is something we'll talk about a little bit more on the next section. Okay, we have one last section for the whole semester. All right? One last section, which is power series. Okay, power series, and I'll save this for the next lecture. And that's it for today.